Our third valid pattern is called the hypothetical syllogism. It looks like this. If we know that P implies Q, and we know that Q implies R, we can conclude with certainty that P implies R. In other words, if P then Q, if Q then R, therefore, if P then R. Right? Here's P, here's R. Basically, if P is Q, if P is true, Q must be true. And if Q is true, R must be true. Therefore, if P is true, R must be true. Okay? So let's say you know, if you get an A in logic, you have a 4.0 for the semester. And you know that if you get a 4.0 for the semester, you're going to be on the dean's list. What does that mean? That means if you get an A in logic, you're going to be on the dean's list. And this is the hypothetical syllogism. Okay, so once again, we don't have to deal with P's and Q's, right? P's and Q's are really just a convention, right? This is also an example of the hypothetical syllogism. This tells us if X is true, then not Y is true. This tells us if not Y is true, then Z is true. Therefore, if X is true, then Z is true. Don't get thrown by the fact that you've got a negation in here. This is still like saying, if P, then Q. If Q, then R. Therefore, if P, then R. Right? We've seen this a lot. In order to get good at using these rules, we need to be able to recognize them when they're not quite as obvious as the simplest example. So here's a more complicated one. A or B implies X and Z. X and Z implies not T. When you put these things together, what do you get? If A or B is the case, then not T is the case. So think of this as P implies Q, Q implies R, therefore P implies R. Let's use our third rule to do a proof. You're given three pieces of information. You're told if A is true, then B is true. You're told if this if-then statement turns out to be true, then E must be true. And then finally, you're told if B is true, then C is true. Now, we've been doing these proofs so far just looking for opportunities to use our rules. That's fine, but there's another way of thinking about these. There's another way of approaching these proofs. What you could do is to think about the conclusion and ask yourself, well, what would I need to establish in order to show that E is the case? Right? In other words, you could try working backwards. So you say, all right, my job here is to get to E, and you look at line 2. Okay, we're kind of lucky here because E appears only once. E appears only once. So you look at line 2 and you realize, well, if I could establish this, if I could establish that A implies C, that would give me E. Right? And so what you've done is you've brought the finish line a little closer, because now your job is to establish that A implies C. Right? Look at lines 1 and 3. Line 1 tells me that A implies B. Line 3 tells me that B implies C. Well, if you put those things together using our new rule, what are you going to get? You're going to get A implies C. Okay? Now, it can be a little challenging to work backwards at first, and if you're not ready for that, that's fine. Okay? At this stage, if you're comfortable just looking for opportunities to draw new information out of the givens, that's perfectly fine. So you might look at this and say, okay, I can put lines 1 and 3 together and I can add to my body of knowledge. What can I say? Well, if line 1 tells me A implies B, and line 3 tells me B implies C, I can conclude that A implies C. And that's our new rule, the hypothetical syllogism on lines 1 and 3. And of course, line 2 tells me if I've established A implies C, as I just have, I'm entitled to say E. Right? What's the justification for now being able to say that E is true? Well, that was our first rule, modus ponens. And we're using modus ponens here on lines 2 and 4. And so what we've done, again, is we've used valid patterns like links in a chain to build and build and build until we get to where we want to be. Once again, this is the hypothetical syllogism.